recording here. So our first reaction type is a synthesis reaction. Again, in general, I would say a synthesis reaction is when you make one product. That's the thing that you should be looking out for more than anything else. How many products did I make? So you can fill in the definition, and then what we're going to do is I'm going to do a demonstration of a synthesis reaction right now. And I gave it to you in word form, but then I want you to write it out with chemical formulas, balanced equations. This one looks a little bit better if I do it with the lights down. But you can see up on the smart board, just like on your paper, I'm going to be reacting magnesium with oxygen. Now, here is magnesium. It's just a strip of metal, silverish metal. So not only can you write down the formula for magnesium right now, but I would like you also to get into the habit of writing down the state of matter. So of the 4 phases I have up on the board, I'm hopeful that you can identify which phase this exists in. I'm going to react it with the oxygen in the air. So you can write down your other product right now, because hopefully you know how to write the formula for oxygen, and you know what phase the oxygen is in. In order to get this to react faster, I need to heat it up, so I'm going to light a Bunsen burner. Oh, that's right, I turned off the gas over the weekend. So, I have my holy can here for a reason. You're going to see why in a second. Okay, it's about ready, and there. It gets really bright, so the holy can helps break that down a little bit. All right, Lexi. Final product looks different than the original thing, right? So a chemical change has occurred, because now it's all white on the outside for those of you who can't see. What state of matter would you call that, Lexi? Solid. There we go. So we write our formula for the magnesium oxide. Let's make sure that we call that a solid then as well. Get the lights back on. We'll move on to our second reaction type. By the way, hopefully we wrote the reaction. Again, I want you to write the reaction. Let's balance it as well. And so part of notes is you guys writing a balanced equation with phase notations. A lot of us aren't balanced yet because we don't have a 2 in front of our Mg. We don't have a 2 in front of our MgO. The next reaction I'm going to show you is a decomposition reaction. To decompose means to break down into its parts. So the key with a decomposition reaction is you start with one reactant. After you write down the definition, actually, let's go over what a catalyst is, and you can fill in that one then, so my slide's a little out of order here. A catalyst is something that will speed up or jumpstart a reaction. So my very bottom bullet point on this slide is what defines a catalyst. It's pretty common for a decomposition reaction to require a catalyst, and the reaction I'm about to perform is no different. Now, once we get the definition of catalyst down, if we go back to my second bullet point, here's the reaction that we're about to do that I'd like you to write down. There's only one reactant, hydrogen peroxide. Does anyone know the formula for hydrogen peroxide? It's a weird one. It's H2O2. Because the peroxide polyatomic ion is O2, and we can't make it HO, because then we'd be changing the polyatomic ion's formula. Notice after hydrogen peroxide, I give the word solution, which means what phase notation should you give? AQ for aqueous. So let's include the AQ after our formula. Again, I want us to get used to this idea of writing phase notations. Now, if it's a decomposition reaction, there's only one reactant. So after you write your hydrogen peroxide, draw your arrow. Above the arrow, you could write down the catalyst, Ki. But again, do not write it as a reactant, because decomposition reactions only have one reactant. So you should have your H2O2 yields, if you want to, you can put Ki above that arrow, then water and oxygen are your two products. Now as you're doing that and as you're balancing that out, I'm going to show you this. I use hydrogen peroxide that is 10 times stronger than what you would buy at Piggly Wiggly. Hydrogen peroxide you buy in brown bottles. To make it look a little bit better, I add dish soap to it, just because oxygen gas is going to be one of the things created, and I want that gas to fill up these bubbles. And then I have potassium iodide solution. Something that doesn't actually react, but it helps start the reaction. It's going to take a second, and now it's going to start creating gas. And as you can see, this dish soap is capturing that gas, creating a whole bunch of bubbles that are going up, 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 and there's a reason why I did this reaction on a tray, because it's going to keep on bubbling and foaming up and up and up. A decomposition reaction, you only make, or you only start with one reactant, but then you make more than one thing. And in this particular one, we made oxygen and water. Hopefully, in order to balance this equation, oh, let's see here, you would have had to put a 2 in front of your water, huh? To balance out the hydrogens and 2 in front of your hydrogen peroxide. You can even see steam being given off in this reaction right now, because heat's generated in this reaction. We're going to talk about that heat aspect of energy of this reaction towards the end of this unit. So there's a decomposition reaction. Now, it's either referred to as single displacement or single replacement. I usually prefer the term single displacement, but just like London forces, dispersion forces, we accept either one. For a definition, it's a single element reacting with a compound to create a new compound and a new element. My second bullet point is something that's already on your note sheet. Next class, we are going to focus on single displacement reactions. And what you will find is not every single displacement reaction occurs. It only occurs if the single element, the element by itself, is more reactive than what it wants to replace. Sometimes I like to use the analogy of, we've got prom coming up in a month, something like that. And let's say that Lexi brings some guy to prom, and they're dancing together, but then all of a sudden, Noah Dorn says, can I butt in? You know, can I have this dance? I mean, there's no way that Lexi is going to be bringing some guy as tall as Noah. So already, Noah's better. Taller is better. Second, the two of you have chemistry together, Lexi. You can't deny it. So she's naturally going to want to make that switch. But on the other hand, if there was some really, really short guy that you had no chemistry with, you would not say, okay, I want to trade partners. You only trade if you're going to trade up. So you don't dump your boyfriend for a guy who sucks. You dump your boyfriend for Noah Dorn. here's the reaction we're going to write. This one I'm not going to show you a demonstration of because you're actually going to do this one next time. Copper. Copper is a metal. So let's write the formula and let's know the phase of a metal. Now silver nitrate's going to be a solution. This one I would have done if we would have had time, but it's just a liquid. Actually, it's in a brown bottle. But it's an ionic compound that's a liquid, so it's dissolved in water. So when you write silver nitrate, which I'll even help you with the formula, is AgNO3. Put AQ after it. It's aqueous. I mean, look at this example. Silver and copper are trading places. Which metal is more valuable? Silver. Which is kind of weird because the copper is the one that's now partnering up. But we'll explain why that is next class period. I'll actually give you a list of a ranking. It's like if the girls had a list of which guys were most desirable, you know, door to door and be on top. We have a list also for which single displacement reactions are most likely to occur. Now, products. Silver, lone element, must be a metal. Copper 2 nitrate. What's the formula for copper 2 nitrate? It's not CuNO3, it's CuNO3 2. Which means now we don't have our equation balanced anymore. The suggestion I gave to a few groups is instead of trying to balance your nitrogens and your oxygens, I bet you have one nitrate, one NO3 on the left side of the arrow, and two nitrates, two NO3s on the right side of the arrow. So balance your nitrates. Put a big 2 in front of the silver nitrate. Now you have two nitrates on both sides. But now you have two silvers on one side and only one silver on the other. I bet you can fix that pretty easily. Okay, single displacement reactions, I will go more into next class because that's our focus next class. Let's move on to double displacement. And again, it could be called double replacement. This is on the back side of your note sheet. Again, we're going to skip example number 2 just to save a little time. So when we look at the definition of a double displacement, I would just first off refer to the fact that it's two ionic solutions and the cation switch places. Do you remember what a cation is? It's a positive ion, cation. Now my second bullet point is already on your note sheet. And that's, hey, if I mix two ionic solutions together, that doesn't mean a reaction actually occurs. One of the products of that reaction cannot be dissolved in water. It creates what's called a precipitate, a cloudy solid, when two solutions are mixed together. And double displacement has its own kind of list of things of whether or not it will occur. If we look at this reaction, so we are just going to do the first example right now. I will help out with the formula sodium chromate. Ready? Na2CrO4. Chromate is a polyatomic ion, CrO4 with a -2 charge. That's why I called it Na2CrO4. This will be a solution. So actually in both of our displacement reactions, the ionic compounds are always aqueous. So let's put aqueous after sodium chromate plus silver nitrate. You should already know the formula for it. It was referenced on the last question. AgNO3. And it is also aqueous. That's why I have solutions after it. Now my products. Notice that I say it makes sodium nitrate solution. So hopefully you can write down that solution. And silver chromate solid. In order for a double displacement reaction to occur, you need to make something that isn't a solution. You have to make a solid. Or it could be a pure liquid or a pure gas. But usually it's going to be a solid. This is another reaction type that there's more that we have to get into. So next week, we are going to be studying double displacement reactions, why they occur, why they don't. I even have a t-shirt for double displacement reactions that I will then bring out. I actually brought it today because I didn't know if I needed it today or not. So again, hopefully our reaction has Na2CrO4 plus AgNO3, making NaNO3 is the formula for sodium nitrate. Ag2CrO4 is the formula for silver chromate. Balancing of this, I bet it's going to require a 2 in front of your silver nitrate and a 2 in front of your sodium nitrate. And then it's balanced. Now these are the 4 reaction types that were on that POGIL packet. The very back page introduces the last reaction type, the 5th reaction type. So again, I'm going to skip example number 2 on your equation sheet. I just want to save a little time. And we're going to go into a combustion reaction. A combustion reaction means we're burning something. And in particular, we would start with some sort of carbon-hydrogen compound. It's called a hydrocarbon. And we would react it with the oxygen in the air. And when they're ignited, when they're burning, because it's a combustion reaction, it gives the same main products of carbon dioxide and water. The reaction I'm going to show you, so this one I do want to show you, is hexane. Remember our non-polar solvent from the last unit? I'm going to burn it in oxygen. So I'm just going to light it on fire. Okay, this one is a little bit better with the lights off, so I'm going to turn the lights off on this one too. So notice again, hexane is a carbon-hydrogen compound. Once the heat source was there, it was able to start on fire because it needed the oxygen to burn in. Our lab benches have a special coating to protect it, so I can start them on fire. I used to do this demonstration a lot more on this lab bench, and the ceiling tiles have a lot of soot, darkness on them from that year after year. So I try to do it on different spots every now and then as well. Now, this is the one reaction type that wasn't in your packet, but it gives the exact same products every single time. Carbon dioxide and water. Audrey, do you notice puddles of liquid on that lab bench? So, if we are to write this equation right now, what phase notation should we give our water on the product side? Should it be an L? No, it should be a G for a gas. It's water vapor. This one is a tough one to balance. So hopefully you have C6H14 as one reactant, plus O2 as your other reactant, yields, that's our arrow, CO2, which is a gas, plus H2O, which is a gas in this case. By the way, phase notations, the hexane is a pure liquid. It's not a solution. Because if it was dissolved in water, it would be harder to light on fire.